Microlecture 33 is an introduction to reaction kinetics. Here we're going to talk about rates and activation energies. Okay, so now we're going to switch gears from thermodynamics and think about reactions in terms of their kinetics. So here we're thinking about how fast does a reaction proceed. And the key idea here is that we really can only make such predictions with sufficient data. So recall that kinetics is all about time and concentration. We collect concentration data, maybe it's concentration of products increasing over time or concentration of reactants decreasing over time. And that's how we come up with a value for the rate constant K. So we might be given a rate equation that is derived from such data. Recall that you guys know what first order, second order, and third order reactions look like in terms of their rate equations. So I could say the rate of a reaction equals the rate constant K times the concentration of A. Right? If you recall, that means the reaction is first order. All right? So this would be, for example, a reaction of A plus B goes to C. The reaction is first order with respect to A if this is its rate equation. Or we might have the situation where the rate of this reaction is the rate constant K times the concentration of A times the concentration of B. The rate is now dependent on the concentration of two of the species involved and its second order. Or we could even see a situation where the rate equals rate constant K times the concentration of A squared times the concentration of B. The reaction rate is third order overall. So those are the considerations we're making here. And what we want to think about is what affects K. What affects the rate of the reaction? What affects the rate constant? And the first thing that affects K is activation energy. We're going to be thinking a lot about activation energy. So if I draw my energy diagram curve, so this is a reaction progress across the x-axis and energy increasing up the y-axis. We've had this energy diagram up on a previous video, but now we're focusing in on a different region of this energy diagram curve. Right? So we understand we're starting with the reactants and we're ending with the products, but it's this change in energy right here that we want to focus on. Right? And so that change in energy is the E sub A, or activation energy of a reaction. It's describing how much energy we need to put into the reaction to get it going. And so we can compare activation energies graphically. We could compare this situation to the one where we start in the same place, but really there's not as much of a hump to climb up over energetically. And so this change in energy is smaller. This reaction, this second reaction, would proceed faster because it has a small hump to get over in terms of energy, and the reaction with the larger activation energy would proceed slower. So what else affects the rate constant K? Well, we know that temperature affects the activation energy because more molecules have the energy required to do the reaction at higher temperatures. Another consideration is sterics and conformations. So we've been talking a lot about how molecules can rotate about their bonds When we talk about Newman projections, we've talked about different conformations of cyclohexane chairs and how rings can pucker and bend in order to form a more stable conformation. And so if the less stable conformation is reactive, then the molecule spends less time in this conformation. Let's think about that. If the less stable conformer is reactive, the molecule spends less time in that conformation. This has the effect of decreasing the rate of the reaction. The reaction will proceed slower. And then lastly, catalysts can affect the rate of the reaction too. To demonstrate this, I'll draw a reaction energy diagram curve and show you how a catalyzed reaction would look different. We'd start at the same energy, we'd make the same products, but the hump to get up over is going to be smaller for the catalyzed reaction than it would be for the uncatalyzed reaction. And we'll see this a lot. We see it a lot in biological reactions that catalysts will do this.